Good morning, everyone. Today I'm just going to quickly go over the chapter on phase transformations. It's chapter 12 in the 9th edition of Callister. And the beginning part of phase transformations is about the kinetics of phase transformations. So that's just the first 4 sections of the chapter. But please note in the study guide there's a large section that we leave out that's got to do with the nucleation, the details of the nucleation of the reactions, and we don't go into that detail. Okay, so first of all, what are phase transformations? They typically are reactions that cause the microstructure of your material to change. So examples of this could be a diffusion-dependent transformation where there's no change in composition or the number of phases. So for instance, if you've got a piece of metal and it melts at a certain temperature or it solidifies at a certain temperature, the composition doesn't change, but it changes from one phase to another. Or, for instance, as we've done in the iron-iron carbide phase diagram, when you've got a polymorphic transformation from alpha ferrite, which is BCC, to gamma austenite, which is FCC, and that occurs at a single composition, and if it's pure iron, that would be at 912 degrees Celsius. That's another example. We also get diffusion-dependent transformations where there is an actual change in the phases that are present. And an example of this would be the eutectoid reaction, again looking at our iron-iron carbide diagram. When we go from austenite and we cool down through the eutectoid temperature of 727 degrees Celsius, if we are at the eutectoid composition with 0.76 weight percent carbon, then we immediately go into two phases, alpha ferrite and cementite. And when I say immediately, I mean at this temperature. But it's not an instantaneous transformation. It takes time. And that's what we're going to be looking at today. Another type of transformation is a diffusionist transformation. For instance, when martensite forms due to the quenching of austenite. But we'll go into that later in the chapter. So how do these phase transformations occur? You do well to read the first paragraph of section 12.3 here, because it gives a very nice and detailed explanation of what I'm just shortly summarizing here. But most phase transformations occur according to time. They're time dependent. They don't happen instantaneously. And usually what happens is that once you activate the reaction, then you start to get small particles or nuclei of whatever your new phase or phases are forming. And this is called the nucleation part of the reaction. And then they start to grow. And as they grow, they eventually transform the whole microstructure into the new microstructure. And that phase is called the growth phase. So we can describe the kinetics or the time-dependent nature of this reaction by an equation called Avrami's equation. So the Avrami equation is represented by this curve that is shown here. And what's important here is that you start off with your nucleation event. And there's a certain amount of time that it takes for these tiny little particles to form to start off the reaction. And once enough of those particles have formed, then the reaction starts to take off. And it takes off at a relatively slow rate, which then increases over time, and then eventually as it gets towards the end of the reaction, when you've got 100% transformed, it slows down again. So on your y-axis here, you've got the fraction of your microstructure that's transformed, and on the x-axis you've got your time, and it's a logarithmic scale. So the Avrami equation is given over here. Y is equal to 1 minus e to the minus k t to the power of n, and that gives you the shape of the curve that is shown over there. Y is the fraction of your microstructure that's transformed, t is the amount of time that it has been at the temperature for the transformation, and k and n are constants that are given by the temperature at which the transformation has taken place and also whatever is transforming. So the rate of the reaction is given by the half time. The half time of the reaction relates to, over here, you've got 50% of your microstructure that's transformed, and the time that it takes for 50% to transform is given over there. So the time that it takes for 50% to transform includes the nucleation time as well as the growth time that it takes to get to 50%. And that gives you what's defined as the rate of your equation. So an example of this Avrami equation on these transformation curves is given here. It's for the recrystallization of copper. So in this case, copper would have started off being cold worked. It's been plastically deformed, and now you're heating it up to different temperatures and waiting until the whole microstructure recrystallizes. In other words, it goes from long deformed grains because it's rolled, and the recrystallization event occurs by tiny nuclei forming, and then those growing into those stress-free equiaxed grains of the recrystallized microstructure. So for instance, if we look at a high temperature, 135 degrees Celsius, you'll see that it takes just over, let's see, 1 to the 0.1 minutes to form enough nuclei that the reaction starts to occur and transform. Halfway through the reaction, we are here at about 10 to the 0.9 minutes, and the full microstructure has transformed when we are at about 10 to the 1.2 minutes. We've got the full transformation. But for instance, if we had to perform the recrystallization at a lower temperature, for instance 43 degrees Celsius, then the nucleation time is much longer. It's over 1,000 minutes, and the time for it to transform takes much longer too. The whole transformation is only complete when we're at about 10 to the 4.3 minutes. We've got complete transformation. So the nucleation takes much longer, and the reaction takes much longer. The rate of this reaction would be 1 over 10 to the 0.9, whereas the rate for this reaction would be 1 over 10 to the 1.15, for instance. So that just shows you how these curves can be read, and that they then bring in, you get different Avrami equations and different curves at different temperatures for different reactions.